Okay, yeah, can you hear me?
Yes, clearly.
Yes. Okay, yeah, thanks for the invitation. And as it was introduced, it's about my talk is about cognitive modeling of human translation production. I would like to um, uh, talk about several things. First, I would like to introduce the area of translation process research, since it might be the case that not everybody is aware of this. The way we acquire the data, we visualize, and then we treat the data. Then I would like to show some ways of how this data was analyzed. And my focus then will be on integrating an annotation that we recently developed. Is this HOF, H-O-F annotation schema, hesitation, orientation, flow annotations in the translation process data, and join this with the task segment framework that was recently suggested by Munoz and Apfelthaler. So these annotations I would like to integrate into an architecture, into a hierarchical architecture that goes along with active inference. Okay, so short overview over the history of translation process research. It started around 40 years ago with think aloud protocols. That is, the idea was these researchers were interested in figuring out what happens in the mind of translators, what happens when translators translate, where do they have problems, where does the translation go smoothly, and so on. And the method at this time 40 years ago was think aloud protocols. So translators would speak out while they were translating what kinds of problems they have, what solutions they would find, and so on. And these protocols would then be transcribed and analyzed, for instance, by Krings or Löscher. And it's a very laborsome activity to transcribe these spoken reports and so on. Then 10 years later, around 1995, Antluke Jacobsen developed Translog. That was a program to log keystrokes. By then, most translators would type in their translation on their computers, on their PCs. And this Translog program would then record keystrokes in time, so keystrokes with a timestamp that could be replaced and analyzed. And this runs in the background, would not disturb translators so much in the typing process. That led to a couple of interesting research activities from 1995, and in 2005, eye tracking technology was added to that process. Means an eye tracker would record where the translator is looking on the screen, and the keylogger would record what the translator types out. So we would have an input into that black box and an output, and then one could try to model what happens in between and so on. So in 2010 around, I joined this Copenhagen Business School. That was where this research took place. And by then, a couple of these sessions were recorded, and my idea was to gather all these different translation sessions in one database, and that was the starting point of the translation process database, translation process research database, which would then, yes, collect all this data, have some compilation into tables that could be more easily analyzed with features and so on. And this activity has gone on in the past, since then. And in 2018, we had a workshop, a boot camp in Macau, where we introduced a browser interface and a Jupyter and Python interface to this database, and that has developed since then into what we have now, and that what I would like to present later today. Because we had this Python interface and also an R interface, I like to call this translation data analytics, because we used many methods from data analytics, and the database was huge. So So that was since 2018, and I will come back later a little bit, talk about the contents and the development of this database. But first, let me show you how we record this data. So this is a translog with an eye tracker. So this translog screen has two windows. In the upper window here, we have the source text. In the lower window, a translator would type in their translations. And then this is an eye tracker tool where we have these light bulbs here. These light bulbs would emit infrared light that would be reflected in the eyes. And then there are cameras here. They would detect where on the screen the translator is looking. And then we have in Translog itself, this is the Translog program that has a gaze to word mapping mechanism, means it would map on the words. So the fixations, the XY positions that the eye tracker returns would map onto the words that are looked at. So we collected a large number of data with this software tool, and it went through a couple of instantiations. And one way to visualize the data are translation progression graphs, like shown here on this picture. This picture shows a translation session of a source text here on the left side. This is the source text of about 160 words. And on the x-axis, on the horizontal axis, is a time scale. So this whole thing is 440 seconds, which is 7.5 minutes about. So this graph represents 7.5 minutes of translator activity in which this text was translated from English into Danish, I believe. So we can see here first we have an orientation phase, and in blue, these blue X's here are fixations on the source word. So we can see each of these fixations, each of these X's is a fixation on the source text, and we can see here that a translator quite carefully reads the entire source text. Then we have this drafting phase where a draft version of the translation is produced, and in green are fixations on the target side. And we can see how the eyes goes back and forth between the source and the target. In black, we have insertions, and in red, deletions, and so on. Once the text is drafted, the translation, then we have here a revision phase where a translator goes again over the translation, going from the source to the target and back and forth, and doing some amendments of the text. So this is one way of, one profile, say, of a translator where we have these clear phases, 3 phases of a translation. Others, translators work in different styles. This translator here, same idea. On the left side, we have a source text, not all words are shown here. And on the right side, we have the target text, which is Spanish in this case here. And we have these word alignments. Sociology is translated here into this word. So we have each line is kind of a source word with their translation. And here on the blue dots, we can see that this translator reads 1.5 segments, then types in the translation here, reads 1 segment again, and then quite smoothly types without much reading ahead. So this is what we call a head starter, immediately typing out with very little look ahead. Quite fluent typing. Okay, so now if we look into this part of that translation session, we can zoom in here. Same picture. Here we have the source text, and here we have the translation into Spanish. As you can see, the Spanish version is, of course, in the syntactic, in the order of the source of the English source text. And what we can see here is that there is some kind of reading, the translator tries to get acquainted with fixations only on the source text, on this segment here. And then quite some fluent typing with the eyes on the source text, starts typing, and the eyes stay on the source side. Then we see here some deletions. There's obviously, or apparently, some kind of hurdle or problems, some typos. The translator types in this O here, deletes it again, types in TO, deletes it again, and so on. And here we see the translator looks at the target side, at the target window, to monitor maybe what happens there. And once this is overcome, it then continues here. Here again, we see many fixations on the target side, many refixations on the same word around norms, right? So this is the norm. So there seems to be a hurdle, and there's in red here deletions. Once the problem was overcome, the translator goes on, reads the next text, and goes on producing the translation. So we can chop up, so we can see that there are two streams of data, right? One stream is the keystrokes, what the hand do, and the other stream is what the eyes do. And the eyes can move from the source to the target, back and forth, while the hands type in some translations or they pause. And here, these lines above here indicate this pausing and keystroke activities. Here we can see these gray boxes are sequences of coherent typing. So these are all keystrokes in a row with no pause that more than 1 second, means that these white stretches here are pauses, keystroke pauses, where there is no keystroke for more than 1 second. Again, typing, pausing, and so on. So basically means that translations emerge, or all kinds of writing activities in terms of pausing and typing. And these sequences, so pausing and typing, have been called translation units. And the idea or the assumption is that in these pauses, some kind of thinking takes place that somehow relates to the typing that follows. And these two kinds of pausing and typing belong together and make up one translation unit. Then we see here below the eyes on the source text in blue, right? And on the target text in green. So the eyes go from the source to the target, source, target, while the hand types in or stops, pauses. So we can then chop up this whole process, this whole stream of data, in finer grained units, and which we refer to as activity units, AUs. And we can see here that we have an activity unit of type 1, where the eyes are on the source text only. Here, an activity unit of type 2, where the eyes are on the target text. We see in green the target text fixations. And then we have concurrent reading and writing, where we have the eyes on the source text while reading, or on the target text. We have the eyes on the source text while typing, and here we have the eyes on the target text while typing, which are activity units of type 4, 5, and 6, and so on. So this more recently, we had still different kinds of an annotation of the data. So while these activity and translation units are produced automatically, so we know when the eyes go where on the screen. Here we have an annotation that was done manually. We have these phenomenal state that give indication of the experiences of the translator's feeling. And the idea was that a translator may feel a need to get some orientation, to feel more comfortable or more acquainted with the text. And then we see this kinds of orientation, and translator tries to orient themselves in the source text while reading something. So we call this an orientation phase. And then we have a flow state, and where a translator is in flow, typing fluent translation, and being immersed in the translation activity. And we have a third state where some kind of surprise. So the translator is surprised by something, hesitates. We call this a hesitation, a state of hesitation, where some kind of a translation hurdle pops up that needs to be overcome. We see here many refixations, in this case on the target text, some modifications and so on. And then here the translator comes again into a flow state, orientation phase, and so on. Okay, so we have 3 different ways of annotating the data. And I would like now to talk about a little bit of the analysis of this data, looking into microcycles and some ways of models, how this has been modeled, this data. So one way of analyzing the data is shown here on this slide. So where we can say that we have these 4 states. A translator can read a source text. Okay, so this would be the AUs of types 1, source text reading. They can read the target text. This would be the AUs of type 2. They can write. So this would be the 5 or 6, where the translator writes something, or they can pause. So means pausing is where we don't have any data. So a translator may look out of the window, for instance, and so the eye tracker would not produce any kinds of data, and we don't know what the translator does at that moment, and also not produce keystrokes. So we call this pausing. So a translator in this kind of analysis can be in 4 states here: reading, source text, target text, writing, or pausing. And there has been some some work about analyzing this, and I think the output, one output of this work is that more experts, if translators are more experienced, we see more often a switching from source text reading to writing. So they would switch around here for source text reading and writing. If the translation becomes more difficult or the translator is less experienced, we see more back and forth between source text reading and target text reading. And for post-editing, we see here going back and forth between the target text reading and typing. So there were a couple of papers exploring this analysis. So this is kind of a flat analysis. So all these kinds of all these units here are on one level, right? Then there could also be a multi-level kinds of an architecture, like shown in this picture here. Here is the idea that an author somehow produces a source text, and according to relevance theory, a reader has this explicature, so what is explicitly encoded in the text, but also takes into account the implicature, so the context in which this text occurs, and so on. And to understand the text, both kinds of explicatures and implicatures need to be taken into account. And this needs to be transferred into the target language. And according to some of these theories, this happens on several levels, or here on 2 levels. On one level, we have a kind of a stimulus mode, where a translator looks at the surface of the stimulus and transfers this into the target language. But then there is a monitor running in the background, in the back of a translator's mind, somehow, that checks for the similarities of the explicatures and implicatures here in the target text, according to this relevance theoretical principles of communication and cognition, which I would like to go into right now. But this kind of process is to check whether these explicatures and implicatures are similar, can be called monitor processes, and the translator would interfere if they notice that something does not does not fit into this picture here. So there's a couple of different authors who have similar ideas. For instance, also Pim, he calls this cruise mode and bump mode, where he says the cruise mode is the default category. So that means the translator is smoothly typing and so on. And until there is a bump, he says, and attention is required and something needs to be done. So this would be then what maybe we called previously hesitation state of hesitation. So a translator hesitates and it becomes a little bit bumpy, and then Pim suggests a couple of strategies to overcome this bump mode. Here he has 3 strategies and 6 different ways to overcome this, from more easy to more complex processes and so on. Okay, and then the most recent way of analyzing this data, so the pause analysis, in my my knowledge, is Munoz and Apfelthaler, who suggest this task segment framework. So they also look into pauses of different delays, and they make a differentiation between 4 types of pauses, 4 durations of pauses. Here, delays, they say basically the translation or typing activities happens in terms of motor programs. So small motor programs are 3 to 4 keystrokes that happen quite quickly below a threshold of 200 milliseconds. So each keystroke in these kinds of motor programs, each inter-keystroke interval is less than 200 milliseconds. And several of these motor programs then cluster into one task. And these tasks, they say, are separated by what they call a respite. And I will talk about this in a moment. These respites are separated by two times median within pause inter-keystroke intervals. But the point is that these respites are non-intentional. So there are little disturbances, maybe these typos that we saw where the translator then needs to look on the screen, or maybe they need to find some keys, or something happens, some distraction from outside. So these are non-intentional halts, breaks, and they have this duration, and they distinguish this from task segment pauses, which they calculate as 3 times median in between inter-keystroke intervals. And these task segment pauses are conscious according to Munoz and Apfelthaler. And in the sense that a translator pauses and has some thought or some reflections and so on. And then a 4th kind of pauses they mention very briefly is super pauses, which are still longer than those, significantly longer than these task segment pauses, which they call super pauses. And I take it that they may relate to what we called orientation phase in our Hove analysis. Okay, so how can we model this with the data that we had previously? So to put these different kinds of annotations into a picture and to see how they relate to each other, I would like to take up this picture, this small graph here again. So we saw before that we have here a small orientation phase, right? Then we have here a kind of a flow state where the translator types in fluently. Then here we have a hesitation with many refixations and so on. Here again, the translator comes into a flow state, and then orientation and flow again. And if we overlay all these different annotations that we have, then it might look something like this. So see, it's the same picture, it's just with these different colors on top. Here we have these we have these phenomenal translation states where we have this orientation first, then we have the translation flow, a hesitation flow, orientation flow, and so on. And then we can further fragment this flow state into task segments. That's what Munoz and Apfelthaler suggest. They are separated by task segment pauses, which are here a little bit in this pinkish color. Okay, so and which are 3 times the between word pauses. So a translation flow can then consist of 1 or more task segments, and each task segment contains a couple of tasks. And each task here is separated by a respite. So these are task segment pauses here, right? And then we have here respites. And okay, so we see a hierarchical picture in some way. Tasks are embedded in task segments, are embedded in a translation flow. So let's look into this small segment and see how those different pause values can be computed. The first thing that we can see by looking into this little segment is our observations. Our observations are keystrokes and gaze data. And then we have the keystrokes here. They produce words, target words, and these can be clustered into what we call alignment groups. Here, this small segment here shows the translation of the breakdown of traditional norms into Spanish, la rotura de las normas tradicionales. So we have an inversion, a syntactic inversion here. Okay, so adjective and noun phrase are inverted in Spanish. So the adjectives comes after the noun here, and you can see that the translator types in the order of the Spanish, the order of the Spanish target text, reversing here the syntactic order. But we can also see that we have to try, keystrokes of different types. We have so within word keystrokes and in between word keystrokes. And this graph, then this picture shows the word boundaries. So we have, if we take these keystrokes to represent word boundaries, so means this quotation marks, a dash, an underscore, all these punctuation marks, and the blank, and so on. They are marked here, okay? And we can then compute the inter-keystroke pause for the keystroke, for these word boundary keystrokes, and all the other keystrokes that are then not necessarily within word boundaries. We call this within word pause. These are which are here, and the between word pauses are the black, marked here in black. And the idea is that a translator or a typer would usually type out, so a word reflects somehow an idea. And once the idea is made up, a translator would more fluently type a word within, so the keystrokes within a word, than between the words, right? So the between the words, there is potentially a new idea that comes up where potentially there is more reflection and a longer pause. So the idea is that the between word pauses are on average longer than the within word pause. And indeed, we can verify this. This is the case. So we can, Munoz and Apfelthaler suggest these two kinds of pauses. The one, the respites that separate tasks, and this task segment pauses separate task segments, and they compute this respites based on twice the median within word pauses, and the task segment pauses 3 times median between word pauses. They don't give really clear reasons why they do this, and what exactly is the reasoning, but let's just assume for the moment, let's take these values for the moment, and also the assumption that these respites are involuntary, so non-intentional, whereas these task segment pauses are intentional breaks, where some higher order stuff goes on perhaps in the translator's mind. Here, then we can further make a distinction between different types of tasks. So we can look into the keystrokes that are realized within one task. And here we can see there's additions only. So there's only additions in this task. Here in this task, there is insertions and deletions. So this would be a change, right? A translator changes something here or here. Here's only one keystroke in this particular task, one insertion keystroke, and so on. So we can qualify these tasks in different ways, and thus count or see how different task segments also qualify. So to wrap up this part here, what we can see, what Munoz and Apfelthaler say, that motor programs are the basic things, how text emerge. These motor programs, the keystrokes are fast. All the inter-keystroke intervals are below 200 milliseconds. Motor programs cluster into tasks, and they are separated by these respites. And then several tasks can cluster into task segments. What we have in the output, what we can observe in the behavioral data is thus this sequence of kinds of pauses, typing segments, pauses, typing segments, and so on. These things are then clustered into task segments. That's what they suggest. And we can qualify the task segments in different ways. We can look of what these task segments consist. Are all these tasks that are here all addition tasks, for instance, or changing tasks, deletions? Is there separation? How many tasks are there? How long are these tasks? And so on. They can all be qualified in a different way. Now, if we want to model this, we can take this as a Markov decision process, where we assume that a translator is in a state, taking in some information. During these small respites, a translator takes in information and then switches to the next respite, to the next state, from S1 to S2, for instance, conditioned on a transition matrix here, B0. And this transition here is also conditioned on the task. So the task can be of a different kind, adding, deletion, and so on. And then transition into the next. So we have here some kind of sensory motor integration where a translator looks at or takes in some input, produces some output, takes some input, produces something, and thus there is a kind of a perception action loop. There's a loop within the task segment which integrates on a quite fast level, on a sensory-motor level. Then we have these translation task segment pauses, and Munoz and Apfelthaler say this is a kind of a intentional stop, so a willful stop in where some kind of cognitive processes take place. So we have decision-making, reasoning, maybe that happens here during these pauses. And here we can, in this architecture, we can assume that these higher order processes that happen here initialize some resources for the lower processes. Here, for instance, a translator will be in a certain state, making up their mind what to produce, what translation to produce. And then while transitioning on this cognitive layer to the next state, it's also conditioned on an action, and this action here will lead to an initialization of the resources in this lower, in the sensory motor layer, initializing these resources here. Okay, so we have here two embedded layers, a cognitive layer and a sensory motor layer, and on top of all this, we still can have here a phenomenal layer where a translator can be in a state of an orientation, or here in a flow state, being in tune with the typing activities and so on. And we can see then switching from one state, from one phenomenal state to the next one. Here, the translator in the flow states will initialize also somehow some kind of resources here and trickle down these initializations down through the process. Okay, so how could this be empirically evaluated, this model that I've just shown? How can we set up and initialize these different parameters? I would like now to go in my next part into exploring this a little bit. But to do this, I would first like to talk a little bit about the CRITT Translation Process Research Database, then look into the distribution of keystrokes, and then come back to the task and task segments, how they can be retrieved or maybe fleshed out through the data from this database. So the translation process research database is, as I mentioned earlier, a database that has now, well, started around 12 years ago or so. By now, it has more than 90 studies are there. These studies are organized in terms of sessions, so each study can have several sessions. Now it has more than 6,000 translation sessions, so a session would be a small text to be translated, so something that we can visualize on these translation progression graphs that I showed earlier. And all these translation sessions have key log data, and many, if not most, of these sessions also have eye tracking data. It consists, so this makes up several hundred hours of translation work, so translators' work, hundreds of translators, mostly students because they're more easily available, but also some professionals, some very highly skilled professionals also. We have translations into more than 10 languages, mostly from English into all these languages that you can see here, but also some sessions into different other languages. Then we have different translation modes. Some of it, or I don't know, maybe quite a lot is from scratch translation, means the translator types the entire text. Some of it is also post-editing, but we also have spoken translation, interpreting, side translation, and translation dictation, and so on. All this is documented on this website, on this CRITT website, and you can find more specific information about these individual studies there. This database is publicly available. It is uploaded in SourceForge. It's free of charge. There is a part that is publicly available. Other parts are still under construction, or some researchers work with the data, which is not publicly available. The data is, all the data is aligned on a segment level and on a word level. So yes. And from these alignments and the different kinds of, from the gaze data and the alignment data, we extract several features, so several tables with features that allow us to have a very rich view on the processes and the product that has emerged. It is possible to have a personal account for this database, also to upload data and to work with this data with our Jupyter and Python and R interfaces and use some of the scripts that we have. Okay, so this is the database. And in order to look at this study or this investigation that we did do right now here, I've pulled a couple of sessions from English into these different languages: Arabic, Danish, German, Spanish, and Hindi, from this database, and looked into the inter-keystroke intervals. So all these data here, it says it's 40 sessions, the number of sessions, Arabic 40 sessions, Danish 69, and so on, the number of sessions for these different languages. And then the number of translators who have produced these sessions, total duration in hours of this data, and the number of inter-keystroke intervals, means basically the number of keystrokes. So this data has 37, the Arabic data, more than 37,000 keystrokes. And you can see here that the distribution of the keystrokes in the inter-keystroke intervals, most keystrokes are around here, between around a little bit less than 150 milliseconds for what is it, Danish and Spanish, here also for German, and for Arabic and Hindi, it's a bit over 150 milliseconds, most of the keystrokes. But you can also see that, that this is much flatter for Hindi and Arabic, the distribution, while it's much more peaky for Spanish and for Danish, and German here somehow in between. So you can see here, these are the median values for these different languages, and these are the means as they are noted here. Okay, so you can see that there is a substantial difference in this translation speed between these different languages. So this was the basis for our analysis, and we took then went on to analyze Spanish and Arabic for this study, and computed these respites and TSF pauses, the task segment pauses, as discussed previously. So twice the within word pause and 3 times the in between word pause. And you can see that also here for these pauses, the Spanish data is much more peaky, and the Arabic data is much flatter distributed. It's longer. So the pauses, the respites and the task segment pauses are longer for Arabic than for Spanish, and flatter distribution. Here we see the correlation between the respites and the task segment pauses for different translators. So we have 22 Arabic translators and 32 Spanish translators. And on this chart, on this graph, each translator has is marked with a certain dot here. For instance, this is the Spanish translator P11. The respites, the average respite, or the respite, the average, the median, twice the median of within word pauses, right, is here a little bit more than 200 milliseconds, and the task segment pause below 500 milliseconds. Whereas for this Arabic translator here, for instance, the respite is more than 1 second, and the task segment pause almost 2.5 seconds. But the thing is here that we can see that each translator seemed to have a certain point. So these two kinds of pauses seem to be discriminating between the different translators. There is, for Spanish, we can see also a correlation between these two pauses. For Arabic, there is no correlation, no significant correlation between these respites and these task segment pauses. Now, so this only shows the length of the pauses, right? Now, if we look into the keystrokes, into the typing activities, we can also make a distinction between the Arabic and the Spanish version of it. So here we see so remember that the task is a sequence of motor programs according to Munoz and Appeltaler, 3 to 4 keystrokes. And here we can see that one task has between here 5 or 6, something like this, keystrokes to maybe 8 for Spanish here, a little bit more, 10 keystrokes. So that indicates that perhaps on average a task will have, if this is true, so 2 to 3 motor programs will be accumulated in one change segment, and in the deletion and in the adding segments a bit less. What is also interesting to see here is that Arabic tasks take on average longer. So you can see here the change, for instance, is 2 seconds, while for Spanish it's a little bit more than 1 second. So the task's duration is longer, but the number of keystrokes produced in the Arabic task is less than in Spanish. So means that, well, as we already saw in the previous data, that Arabic translators are not as fast as Spanish translators. This graph also shows that we have here, it puts into relation the duration of a task and the number of keystrokes within that task. So all tasks together. And we can see here that we all again see a clear distinction between different translators. So this Arabic translator has a much flatter line here. So whereas these two Spanish translators seem to work in a little bit similar mode, means they produce the number of keystrokes per duration. There's a quite strong correlation between the duration and the keystrokes within a task, 0.98, which indicates that the translator types are kind of consistent. So within the keystrokes within a task seem to be quite consistent. The intervals, the inter-keystroke intervals of keystrokes inside a task seem to be consistent and typical for a translator here. There's a variation across different translators, but within a translator, it seems to be consistent. Here we see now the attributes for a task segment pause. And we can, so what it says here on this side is the sequence of tasks within one task segment. In these two, okay, like this, right?
Yes.
There again.
Yeah.
Okay. So, so I was talking about. So I talked about previous in the previous slide. I talked about the task properties of the tasks, and now I would like to talk about the task segments, and then come to the host states. So here, this table shows some properties of the task segments, and they are all together in this Arabic and Spanish data. We have 10,356 task segments, and these are the 11 most frequent tasks in these task segments. So here the task segment consists only of one single task, here of two addition tasks, here of a deletion task, and so on. And you can see that about 30, almost 40% of all the task segments consist of a single insertion task for Spanish and for Arabic. Okay. So that gives us some idea, and there are almost 900 different task labels, but most of the labels only occur once, and you can see that the 75% are here. These 11 labels make up 75% of the task segments. Now, if we look back, remember this graph here. So we have these different states: orientation, flow, hesitation, and so on. And we manually annotated host states for 8 English Spanish translations and for 6 English Arabic translations. Each of those texts has 150 words altogether. I think there were almost 1,000 words or something, a little bit more. And we can see here the number of states: hesitation, orientation, and flow states that were annotated in these translation sessions. So note that these are manual annotations, and the other annotations, so figuring out the task and this task segment, that can be done by a computer program, so algorithmically, right? So computing the interword median interword ratio and so on is something that can be done automatically. But this orientation here, these phases here, translation states were annotated manually. And we can see on this graph here shows that the most likely probability is for a translator to go from an orientation state into a flow state into an orientation state. So here, if, for instance, the translator is in an orientation state, then with 80%, 85% almost probability, the next state will be a flow state, and only 16% hesitation state. And this is the case for Arabic and Spanish, very similar, so that the most likely, the most frequent pattern will be an orientation flow orientation state. Now, if we look into the task that occur within hesitation and the flow state, we can see that 85% almost of 84% of the tasks within the flow state are adding tasks, so insertions. The translator inserts, and this is the case for Arabic and for Spanish. And the other, so 8% for deletions and change states, whereas in a hesitation phase, a translator would approximately 50% only engage in adding stuff, but much more frequently into deletion and changing, which makes sense basically because in a flow state, a translator would just produce text, whereas in a state of hesitation, they would delete and change things, right? So now if we look into the labels here in the flow and in the hesitation state on the task segment levels, then we can see that we have here the 5 most frequent task segment labels, and they are exactly identical for Arabic and for Spanish. So they are all insertions here, adding segments, whereas for the hesitation state, we have the most frequent task segment is a single adding task, a deletion task, and the second most frequent. Then we have 2 adding tasks here for the Arabic, whereas for Spanish we have a change and so on. So, but all this, if you look at this one here, there's just a reverse of the 2 ranks here, but the correlation is very high. So the correlation between the sequences of the task segment labels between the Arabic and the Spanish is very high, basically indicating that Spanish and Arabic translators engage in similar activities in the flow and the hesitation state, despite the fact that the inter-keystrokes intervals are also very different in these 2 modes. So I would like now to come to my last part of this talk and see. So I started out with pointing out the task segment framework and the whole framework, then how this data can be interpreted as a hierarchical architecture. I pointed out how we can retrieve this data, these pauses, and in the translation process database. And I would like now to come back to look into what all this has to do with active inference and this architecture here. So this is a slide that I showed earlier, where we have these different layers, sensor-motor layer, which produces basically this perception action, very integrated fast perception action layer, a cognitive layer, and a phenomenal layer. We also did talk, I talked a little bit in the beginning about these input. We have here observations, so that means gaze data. Translator would read something, type out something, and there would be in a kind of a loop of action, perception and action, where of course they would also revise what they have done and control what they have done. But then this graph suggests that we also have input here in the cognitive layer and in the phenomenal layer, which are taken directly from the output. So here the observations here are on the interface, right? So the translator looks at the screen at the output of what is being typed, and this output, this observation could then be analyzed concurrently. This architecture suggests on these different strata, layers of the mental processes. So it could be the case that that on the sensor motor level, some kind of analysis takes place with respect to this input that is being read. At the same time, concurrently, another kind of analysis happens on this cognitive layer, where memory retrieval or thoughts will happen, and on this phenomenal layer, where some kind of feelings and expertise experiences are triggered. So this architecture would suggest that these upper layers here would initialize the resources of the embedded layers. Okay, so in a kind of a trickle down, the initializations of these resources here, whereas the observations only can happen from the very output. Means that the upper layer, for instance, this phenomenal layer, can allocate or trigger some resources in this cognitive layer, but does not have direct access to what happens in this layer, right? So it can only have access, it can only know what these embedded layers produce by looking at the output, what they actually produce. in contrast, this architecture would then suggest that there is a kind of a bottom-up information from the embedded layers to the upper layer, right? So the sensor-motor layer can inform the upper layer, the cognitive layer, about the status. So this upper layer has control over what happens inside. And same here. And maybe also one could draw a line here. So this would make it possible what people refer to as metacognition. So this cognitive layer has some information about the embedded processes here, gets some information, and can reconfigure. So, but it also allows for a possibility, for instance, where some resources are allocated or initialized here, and then a feedback goes up, and there is a loop in between these two layers, which would then produce inferred fantasies. For instance, there can be allocation of some resources, some memory can be triggered, and so on. These memories can trigger some kind of feelings, or experiences, and so on. These experiences then trigger back here some kinds of other cognitive resources, and there could be some kind of loops going around here, right? Which then would lead to inferred fantasies and produce in the end perhaps something in the output that is not very well suited for this output. Another possibility for an architecture here would be where we have both possibilities, where we have these internal feedback loops, but there could always be kind of consolidated through empirical evidence what is actually observable in the outside world. Okay, so there's different ways of maybe conceptualizing and this architecture, and then we also can think of an initialization across different layers. So this phenomenal layer could, for instance, instantiate these sensorimotory layers here, in addition to these cognitive layers. So the last point that I would like to talk about is what this whole architecture makes it actually active inference or predictive processing. So these Markov decision processes here, right, they go from one state to another conditioned on the actions and the B matrices. So we have likelihood of recognition here, a likelihood of action, and then we have a kind of a prior and a set of states. But now what makes this thing active inference is that we have also a look ahead. So there is a possibility here for predicting or for predicting the future and for having some preferences for outcomes. So assume that a translator is in this state 1 here and produces is engaged in producing this task 1. Okay, so there will be in one state in one state here in producing an output, but at the same time a translator can already think ahead. So in this traditional way, in this transition here, the transition would only depend on the state before and on this B0 matrix, on this transition matrix. Here in this expected free energy active inference framework, this transition also depends on expected preferences and expected output. So a translator might think about in the future what is the best possible transition into a future a translation process, and then decide those transitions based on a minimization of the free energy that is encoded in these transition states. Okay, and that's basically what I wanted to say. So I have tried to give an outline of an active inference agent for simulating variations of translation processes. I have tried to integrate here the task segment framework from Munoz and Affelthaler and our own annotations of phenomenal state, and this architecture that I have suggested here depends on these three kinds of embedded layers and the properties of tasks and the task duration respites, and then the properties of task segments and task segment pauses, and on a third level of transition probabilities of these host states. So the next steps would be to think about more carefully the various architectures that I've pointed to, the various implementations and the implications that they would have, the different bottom-up and top-down implementations, and then in particular also the role of expectations and translations predictions, and what the how we can initialize and measure these different ways of implementing this. Finding evaluation criteria for this whole architecture will be another issue. And currently, we're looking into gaze classification of gaze patterns so as to integrate these gaze patterns into these architectures. Okay, so I would like to thank very much my collaborators who are engaged in this work. Masaru Yamada, Takanori Mizowaki, De la Cruz Cabrera is a colleague from Kent State University. Yusheng Wei, who was a postdoc in Kent State, but is now in Hong Kong. And Longhui Su, who is at Kent State University, a PhD student. Okay, thank you so much. And if there's any questions, please let me know and have discussion.
Okay.